California's population was 29.76 million in 1990 and 33.87 million in 2000. Assume that the population grows exponentially. We're going to find the function models the population t after 1990, and so we'll let t be the years since 1990. Even if the problem does not state it, it is better to let t be the starting years in the problem. We're not saying that California start in 1990, and so 1990 corresponds to t equals 0, and therefore 2000 minus 1990 is the number of years since. 2010 years since 1990. So we end up with 2 points basically. T equals 0, the population is 29.76, and when t equals 10, the population is 33.87. We might be given the information in the form of the graph as well. When time is 0, the population is 29.76, and when time is 10, the population, not drawn to scale here, is 33.87. And so we might be given 2 points with an exponential model, and we're looking for this equation that will tell us the population at any time. We start out with a generic population model where the P of t equals the initial population and then b to the t. This is ab to the t, or P of t equals the initial population e and then rt. Usually we will use this model. And so if we were to let t be the year since 1990, then the initial population is 29.76, and so we update the equation right away. P naught is 29.76 e to the rt. Finding this equation is to find the parameter P naught, which we found already, and r. We're going to use the second piece of information to find r. If we plugged in 10 into this equation so that we can replace t with 10, then the outcomes need to be 33.87. And so to find r, we divided by both sides of the equation by 29.76. We then ln both sides of the equation to get 10r equals ln of 33.87 over 29.76, which is still inside the parentheses, and then we would divide it by both sides by 10 to get r by itself. Using a calculator, we will get r to be approximately 0.0129. We want to keep as many decimal places, at least 4, because exponential model is very sensitive to small input. Small changes can give us a very large difference. And so we update the model. It is P of t equals 29.76 times e to the positive 0.0129, because this is exponential growth t. Next, find the time required for the population to double. To double the population is to double the 29.76. The right-hand side is still 29.76 e to the 0.0129 t, and we're looking for the time. When we find the double time, it doesn't really matter what the initial population is, because we can divide it by both sides by 29.76, and that number will cancel out. Even if we were not given the initial value, we can still solve this problem. 2 equals e to the 0.0129t, and so ln of 2 equals ln of e to the 0.0129t, and so ln of e canceled out, and it gives us 0.0129t equals ln of 2. T is ln of 2 over 0.0129, and this is the generic formula for the doubling time. It is ln of 2 over whatever the value of r is. We then put this in a calculator to get roughly 53.73, or about 54 years. We estimate that after 54 years since 1990, the California's population will double. Use the function to predict the population of California in 2010. Now, 2010 is 10 years since 1990. We simply plugged in 10, not 2010, into the equation. 29.76 e to the 0.0129 times 10, and then we put it in a calculator. This gives us 33.86 million people. The actual population of California in 2010, if we were to look it up, it is 37.27, and so we underestimated. If we take 37.27, which is the actual population in 2010, and subtract the predicted value, 33.86, we will underestimate 3.41 million people.